So today we're going to continue where we left off at the last class period. We talked about the different rules for filling up your electrons in the proper orbitals. What we've got here is the orbital diagram for oxygen. We have our orbitals, lowest energy on the bottom, highest energy on the top, lined up. We have 1s as the lowest energy, followed by 2s, followed by the 3p orbitals, 3s, 3p, 4s, 3d, 4p. And we're going to put in the electrons for oxygen in these orbitals. So let's start off with figuring out how many electrons does oxygen have. Oxygen in this case is a neutral atom. So what we do to find out the number of electrons is we go to the periodic table. Oxygen's got an atomic number of 8, which means it has 8 protons, and it also means it has 8 electrons. So we need to put those 8 electrons in orbitals. Because of Aufbau principle, we're going to start off by putting our electrons down at the lowest energy level first. I'm going to fill up the lowest energy level first, and we will put 2 electrons there. One spin up, one spin down. That's due to Pauli exclusion principle. And we'll keep filling from the lowest energy level first. Once we fill up an energy level, we go to the next. Once we fill that one up, we go to the next. If you have some orbitals that are at the same energy level, then you do not pair up until you have to. And that's the Hund's rule. So let's see what that looks like for oxygen. Oxygen has 8 electrons. 8 electrons. So here comes the first electron. It's going to the lowest energy level first. And now the second one's like, oh, there's a second lowest energy. I'm going to go there. Here comes the third and fourth, and now 2s is full. Now we can go to 2p. We got electron 5. We're not going to pair up until we have to. 6, 7, and now we can pair up because this is the only spot where we could pair up. We had no other choice because we have to fill up the 2p before we go up to the 3s. Let's see that again. Okay. First comes the first electron. We go to the 1s. We put 2 electrons there. Then we go to the 2s. This is electron number 3 and electron number 4. Opposite spins. Here comes 5. All these p's are same energy, so we do not pair up until we have to. That was 5, 6. It's electron 7. Now the 8th electron needs to pair up. This is called the orbital diagram for oxygen. Okay, so let's practice. So if we were trying to figure out what is the sub-level filling order up to the 5s sublevel, we could do one of 3 things. I had you write down the orbital filling order on your periodic table if that was something you preferred to do. I also had you write down all the orbitals and then the arrows showing you how you fill up if that's the way you prefer to do it. And we'll talk about that one again in a little bit. But I'm going to show you now how to figure this out for using the periodic table. We're going to try to fill up to the 5s sublevel. That means we're going to go to the 5th energy level, and we're going to go to where s's are. In order to do that, we need to fill up the lowest energy first until we get all the way up until we get to the 5s. Let me show you what that looks like. We have the periodic table here, and we're going to try to go to the 5s. The 5s. That means the 5th energy row where the s orbitals are. Remember, I had you label your s's, p's, d's, and f's. This section right here is your s's. This section right here, which are 6 across, is your p's, the thing that's outlined in blue. Then right here in this section, outlined in orange, that's where your d's are. This is where your f's are. Remember, these numbers here are your energy level. That's your n, first principal quantum number. Okay, we're trying to go here to the 5th energy level, S. But before we get there, we need to go through the whole periodic table until we get there, from left to right. So we're going to start the first energy level. We're going to do 1s. That's the first thing we do. Remember, this helium is the same as that helium. I just wrote it over here. So first energy level, we do 1s. Now our first energy level is full. What comes next? 2.
Where are we here? We're in the S section. 2s. Go all the way across. Look, we have a 2 here. So this is a 2. What's this? P. This section is the P. 2p. So far we have a 1s, 2s, 2p, 3s, 3p, 4s. Now here I had you write this 3D. This section right here is called a 3, and we're in the D section. So we do 4s, 3d. Now we're back to 4. 4p, and then 5s. Let's do that again. 1s, that finishes that row. 2s, 2p, 3s, 3p, 4s, and then it says 3 there, 3d, 4p, 5s.
So this is what it looks like once we've written it out. We went through that's what we did through the periodic table. We went through the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and 5s. Okay, on the next one, I want you to try this. You are trying to figure out the filling order for an atom with 36 electrons. So what atom is that? Well, the first thing you have to determine is who has 36 electrons. When you look, that is krypton. So you need to figure out the filling order to krypton on the periodic table. Okay, so pause your video right now and try it. Okay, welcome back. This is what you should have come up with. 1s, that finishes the first row. Then you go through the 2s, 2p. Now you're done with the second row. Then you go 3s, 3p, 4s, 3d, because you're going across that D block, and we labeled that a 3d. And krypton is in the 4p. Okay. The last question says fill in the 3p sublevel with 4 electrons. Sublevel is an orbital. We're looking at p orbitals and the third energy row. So you have 3 little lines like this. And what that means is you have 4 electrons. This is asking you about Hund's rule. Hund's rule says you do not pair up until you have to. The Pauli says, okay, when you do pair up, make sure the electrons are facing opposite directions, and you can only have 2 per per orbital. So this is like a px, a py, and a pz. We have 4 electrons. How are we going to fill it? We're going to go 1, 2, 3, 1 each level, 1 each orbital. Now we have to pair up 4. That's what it looks like to not pair up until you have to. Okay, just to remind you what an orbital is, you've seen this same slide before. The orbital is a space where there is a high probability that a pair of electrons, remember you can put 2 electrons per orbital, a pair of electrons can reside. It's an area where they might be found. Your s orbitals are spherical. Your p orbitals, of which you have 3, are dumbbell shaped. Your d orbitals, of which you have 5, are complicated shapes, like four balloons tied together. There's 4 of those, and then there's one that looks like a dumbbell with a donut around it. But you have 5 of those, 2 electrons in each, for a total of 10 electrons. Oh, for the p orbitals, you have 2 electrons each, for a total of 6 electrons. For the s orbitals, you have 1 of them, 1 orbital, 2 electrons each, or for that one, and it's 2 electrons. So 2 electrons, 6 electrons, 10 electrons. For the f orbitals, you have 7 of them, 2 electrons each, for a total of 14 electrons in an f orbital space. Okay, so let's go back to electron configuration. Remember, electron configuration tells you how your electrons are arranged. So this is an electron configuration for one of the elements on the periodic table, and we'll figure out which one it is in a second. But the first thing you need to notice is this number 1. We've already done that here. You see that? 1, 2, 3. That's just telling you the energy level you are at. This 1 is your energy level. It's your row on the periodic table. Row 1, row 2, row 3. We also call that a period. As you go across the periodic table, it is called a period. Our possibilities for that number are 1 through 7 in this class. 1 through 7. Okay, the next thing you see is a letter. This letter is your sub-level or your orbital. There are 4 possibilities in this class. We can have s orbitals, we can have p orbitals, we can have d orbitals, or we can have f. That's all we're doing in this class, even though other orbitals do exist. They're not the ground state, which is what we talk about in this class. Okay, the last number you see, it's a superscript, so it's up high. That is the number of electrons you have. Okay, if your letter is an S, the highest that number can be is a 2, because s orbitals only hold 2 electrons. If your letter here is a P, the highest that can be is 6, because you have 3 p orbitals, each with 2 electrons, so 3 times 2 is 6. If this letter is a D, the highest your number can be 10. You have 5 d orbitals times 2, 10. And if your letter here is an F, the highest this number can be is a 14, because there's 7 f orbitals, 2 electrons per orbital, 2 times 7 is 14. Okay? So if we were to look at this element, let's pull out our periodic table. We are looking to see which element this is. Which element has an electron configuration of 1s1? So which element is in the first energy level, is in an s orbital, and has a total of 1 electron. So if you look on your periodic table, the element that has 1 is on the first energy level. It's in an s orbital and has only 1 electron. That is hydrogen. If you were to do the electron configuration for helium, helium has 2 electrons. So here it would be 1 s and then a 2, because helium has 2 electrons. Okay, let's do one a little more complicated. But it's not complicated. Let's do oxygen. Oxygen has 8 electrons. Okay, so let's write our orbital notation. That's the thing with the lines and the arrows. We know, because we just practiced this, we know the order that it fills up. Looking at your periodic table, we know that you go through the 1s first, then the 2s, then the 2p. So if you were doing 1s first, you would we have a total of 8 electrons. You would put 1, 2 electrons there, spin up, spin down. Now this energy level is full. Now let's go to the second energy level and let's look at the s orbitals. So we have 2 electrons so far, 3, 4. Now we go to the p orbitals, p. Okay. These are all equal energy. They're all right next to each other. These are p orbitals. We're not going to pair up until we have to. So we have 4 total electrons so far. 5, 6, 7. See, we haven't paired up, and now we have to pair up 8. This is what the orbital notation looks like. Usually we've been drawing it vertically. It's okay to draw it horizontally if you want to save space. Okay, to write our electron configuration, we would write 1s2, 1s, first energy level, s, how many electrons? 2, 1s2. 2s, second energy level, how many electrons? 2, 2s, 2. 2p, 2p, how many electrons? 1, 2, 3, 4. 4 electrons in the 2p. So this is your electron configuration. But let's go to the periodic table and see if we can get it from there.
Okay, we are trying to go to oxygen. This is oxygen. But to get to oxygen, we need to go through everything else first. So we're going to do, first we're going to go through here, 1s. because in the first energy row, this helium is the same one as over here. First energy row, and we're in the S's, so that's the 1s. How many electrons? 1, 2. So it's a 1s2. Now we finished the first row. Let's go to the second row. We're in the second row, so it's a 2. This is an S. 2s. How many electrons? 1, 2. 2s2. Let's go across. Now we're here. We're in the 2p. How many electrons though? 1, 2, 3, 4. We have 4 electrons. 2p4. So let's try that again. 1s2. 2s. 2s2. 1, 2. 2p, how many? 1, 2, 3, 4. 2p4.
So we were able to come up with the same electron configuration using the periodic table. So there is a built-in check here. We have a total of 8 electrons. If you add up your superscripts, they should add up to 8. 2 plus 2 plus 4 gives you 8. You didn't forget any electrons. Okay. If you don't want to use your periodic table, you can use this thing with the arrows again. You line it up like this, 1s, then you do a 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. The 5s look like the 4s, 6 and 7s do as well. Okay, so when you're filling up, start from the bottom left-hand corner and just follow the arrows, and that will tell you the order you fill in. 1s, 2s, 2p, 3s, 3p, 4s, and so on and so forth. The other thing you can do is just write this whole series on the bottom of your periodic table. I think it's easier to use the periodic table, but you do what works for you. Okay, let's do this for iron. We're first going to draw the iron orbital diagram, or we can also call it an Aufbau diagram. So if you were to write it, iron has 26 electrons. Let's write out, we got to keep track of our electrons. We'll put 2 in the 1s. Next comes 2s. 2, that's 4 total. 5, 6, 7, 8, 9, 10. The P's are full. Now we go to the S3s. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now we go to 3D. 21, 22, 23, 24, 25, and 26. This is the orbital diagram for iron, and it shows the way it fills up. Now, here we've got the same orbital diagram. I've just put it out horizontal to save room. Let's come up with the electron configuration. So we've got a 1s2, 2s, 2 electrons, 2p, how many electrons? 6, 3s, 2, 3p, 6, 4s, 2, and 3d, 6. But we can come up with this on the using the periodic table. Let's try.
Okay, let's try to come up with iron on the periodic table just by working through the pattern. We're trying to go to iron. So we're going to do 1s, 1, 2. Finish that row. Then we do a 2s, because we're in the S section. 2s2. 2p6. That's 6 across. We finish that row. 3s2. 3p6. Now we're in the fourth row. 4s, how many? 2. Now we drop to a 3D. 3D, but we're trying to go to iron, so we're not going to go all the way across. We're just going to stop at iron. So it'd be 3D, how many electrons? 1, 2, 3, 4, 5, 6. So it is a 3D6. Let's do that again. 1s2. Done with that row. 2s, 2s2. 2p6. 3s, 1, 2. 3p6. 4s2. 3d, 1, 2, 3, 4, 5, 6.
We'll now do silicon. So for silicon, first thing you need to ask yourself is how many electrons does silicon have? When you find it on the periodic table, you see that it has 14 protons. We're talking about neutral atoms, so it has 14 electrons as well. What energy level is silicon on? That's a good thing to ask yourself. What is the very last thing that I should fill? What is my last thing I should fill? So if you look at silicon, it is in the P's area, and it's in the third energy level. So the very last thing you should have for your electron configuration or your orbital diagram is a 3p. Okay, so just keep that in mind when you're doing these problems. Okay, so let's do an orbital diagram. So first we're going to fill up the 1s. That's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Don't pair up until you have to. When you go look up your electron configuration using the periodic table or using your orbital diagram, you come up with a 1s2, 2s2, 2p6, 3s2, and a 3p2. Okay, let's do the same thing for zinc, and I will show you this on the periodic table as well. Okay, zinc has 30 electrons. It's got an atomic number of 30. We said this was neutral, or we haven't said it wasn't neutral, I guess is a better way of stating it. 30 protons, therefore it must have 30 electrons. What energy level is zinc on? So zinc is on the 4th energy level. However, it is in the D block. So if it's in the D block, that row is labeled as a 3D. The very last thing you are going to fill up is the 3D. So this is what your orbital notation looks like. We got to put in 30 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That is what your orbital diagram looks like. If you were to write this as a electron configuration, you would write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now let me show you what that looks like on the periodic table.
Okay, let's do zinc. So zinc is right here. So to come up with the electron configuration for zinc, you would do 1s, 1, 2, so 1s2, 2s, this is in the s, 1, 2, 2s2, go across, 2p6, that's 6 across, 3s2, 3p6, 4s2, 3d, and it's 10 across here. 1, 2, 3, 4, 6, 7, 8, 9, 10. 3d10. Let's do that again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
Okay, now pause the video and see if you can come up with the electron configuration for oxygen, sulfur, vanadium, and zirconium. Part of chemistry is searching for things on the periodic table. So you have to find these things. We've done oxygen already. So see if you can do sulfur, vanadium, and zirconium. So please pause the video now. Okay, so let's do oxygen. You should have come up with, because we've done this many times, 1s2, 2s2, 2p6, 2p4. Sulfur has 16 electrons, 1s2, 2s2, 2p4, 2p6, 3s2, 3p4. Okay, 16 electrons. So if you add up all these superscripts, it will add up to 16. Vanadium is in the D block. It's on the very first row of the D block. you should have come up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now it drops to a 3d. How many? 3d3. And the last one is zirconium. That has 40 electrons. You should have come up with a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. I will show you how to get zirconium. I'll walk you through that on the periodic table.
Okay, to come up with zirconium. Zirconium has 40 electrons. We're looking at right here. So to get there, we need to go through the rest of the periodic table. Lowest energy first. So we're going to do a 1s2, 2s2, 2p6 across, 2p6, 3s2, 3p6, 4s2. Remember, we're trying to go to here. 4s2, 3d, that's 10 across, 3d10, 4p6, 5s2, 4d, how many? 1, 2, 4d2. And you should have predicted the very last thing you were going to do was a 4d2, because you can look at that. You can just look at the very last term and know where you're ending up.
It takes a really long time to write all of these things. So there is a way to write a shortcut, and that's what we're going to learn right now. It's called noble gas configuration, noble gas notation, noble gas configuration. They're both synonymous. So what you do for noble gas notation is that you start from the previous noble gas and then you write that configuration. Well, in order to do this, you need to know what a noble gas is. Noble gas is found in the very last column of the periodic table, from helium all the way down. Helium, neon, argon, krypton, xenon, and radon. Okay, those are your noble gases. Those are perfection on the periodic table. Those are the elements that do not need to react because they are content with themselves. They have what's called an octet, and we'll talk about that in a little bit. But noble gases are like the royalty of the periodic table. They don't interact with anybody. They're inactive. They're unreactive. They're inert. In other words, you hear a lot. All elements on the periodic table are their goal in life is to have a noble gas configuration, to have a full what's called a full octet. But regardless, to write noble gas notation, you need to know what a noble gas is. What you're going to do is you're going to start from the previous noble gas of the element you're looking at, and then you're going to write the configuration. So what does that look like? And I will show you on the periodic table in 1 second. But if you're talking about oxygen, the noble gas that comes before oxygen is helium. The noble gas that comes after oxygen is neon. We don't want that one. We want the one that comes in the row above it. So the noble gas that comes before it is helium. You write helium in brackets, and you say the rest of the configuration up to that point is like helium. Now what's left after helium? You write just the row oxygen is in. So you write 2s2, 2p4. In this case, it didn't save you a ton of writing. But if you get to something like, there's sulfur, neon's the one before it. If you get something like vanadium, vanadium was a lot of writing. If we go back to the previous slide, look at all this we had to write for vanadium. So if we were to write the noble gas configuration for vanadium, we would find the noble gas that comes before vanadium, and that's argon. That's a noble gas in the row above it. And then after argon, we write what is left. 4s2, 3d3. That's all we need to write. Let's try zirconium, and I'll show you zirconium on the periodic table. You find the noble gas that comes before it, the one in the row above it. And for that case, it's argon. And then all we need to write is what's left. 5s2, 4d2. Let me show you that on the periodic table.
Let's do noble gas configuration for vanadium. Here is vanadium. Which is the noble gas that comes before it? So in the row before it, not in row 4, in row 3. Who is the noble gas before it? Argon. So you write argon in brackets. When you do that, it says that the configuration, electron configuration for vanadium is everything the same up to argon. And what's left now? All we need to write is argon in brackets, then 4s2, 3d1, 2, 3. And then we're done. Let's try it for zirconium. Zirconium. So you look for the noble gas that comes in the row above it. So this one, that is krypton. We would write krypton in brackets. Then we'd write what was left. 5s2, 4d2. And we're done. Instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2, all we had to write was krypton, 5s2, 4d2.
Okay, the last couple things we need to cover are valence electrons, electron dot, and electron configuration for ions. So let's first of all talk about what valence electrons are. Valence electrons are the electrons in the outermost energy level. They're also called your valence shell electrons. These are the ones that are in the outermost energy level, in the outermost orbitals. These are the ones that are involved in chemistry, because all of the electrons that are in lower energy, all the ones that are in lower energy shells, those orbitals are full. There is no room for an electron from another atom to come in and react. So the only ones that are important in chemistry are the ones that are on the outside, because those are the ones that might have some room for electrons to come in. There is space in the apartment. There's space in the orbital for other electrons. Okay, so those valence electrons are the ones that determine the chemical properties of an element, how an element behaves. Valence electrons are the ones involved in the bonding, the ones that are involved in the chemistry. So when we talk about valence electrons, we're talking about strictly the electrons in the s and p orbitals of the highest energy level of an atom. The s and the p orbitals, only s's and only p's. Okay, so again, electrons in the outermost energy level, they're located in the highest s and p orbitals. So you can have a maximum of 8 valence electrons. Why 8? Because s can hold 2 electrons and p can hold 6. 2 plus 6 is 8. Your noble gases, the ones all the way to the right on the periodic table, all have 8. They're full. That's what everybody strives for. They strive to have 8. That's called the octet rule, and we'll talk a lot more about that in upcoming units. But just know we're trying to get the electrons from the highest s and p orbitals. So let's look at nitrogen's electron configuration. If you look at nitrogen's electron configuration, you have 1s2, 2s2, 2p3. The highest energy level is 2. See, 2. That's your highest energy level. How many valence electrons do we have in the second energy level? Well, we have 2 plus 3. That is 5. 5 valence electrons. Okay, so now let's look at magnesium. Let's look at its electron configuration. Its electron configuration is 1s2, 2s2, 2p6, 3s2. The highest energy level you see here is 3. These guys are full. This one has no room for anything else. This has no room. This has no room. The highest energy level you see is 3. You only have s orbitals, but we have 2 of them. So that's 2 valence electrons. Let's look at selenium. its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Its highest energy level is 4. Even though there's 3 Ds in the middle, its highest energy level is 4. How many valence electrons does it have? 2 plus 4. It has a total of 6 valence electrons. Okay, before we get to the electron dot, let me show you that on the periodic table.
Okay, so let's look at this on the periodic table. If you look at this first column, group 1, it's this guy, hydrogen's highest energy level is 1, and this is a 1s1. Lithium, highest energy level is a 2. It's a 2s1. This is a 3s1. This is a 4s1. This is a 5s1. This is a 6s1. This is a 7s1. Everything in this column has 1 valence electron. Let's look at the second column, with the exception of helium. Helium's over on the other side. Let's look at here. Everything here has 2 valence electrons because its configuration 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. Everything here has 2 valence electrons. Let's go over here. Everything in this column has 3. Everything in this one has 4, 5, 6, 7. Everything in this column has 8, with the exception of helium, which only has 2 because it's in the first energy row and there's only s orbitals available. Why does everything here have 3? Well, let's look at boron. Its configuration is helium in brackets, then 2s2. There's 2 electrons. 2p1. That's 1. 2 plus 1 is 3. Let's look at aluminum. It's got a 3s2, 2 electrons there. 3p1, 1 electron, 3. Let's look at fluorine. Chlorine, bromine, iodine, and I forgot what this guy's called. Regardless, and I've got it marked off, AT. Everything here has 7. Why is that? Let's look at fluorine. 2s2, that's 2 electrons, plus 2p, 1, 2, 3, 4, 5. 2p5, 2 plus 5 is 7. So I would mark that on your periodic table. If you look, I have it highlighted at the top of my table. 1, 2, 3, 4, 5, 6, 7, 8. That is the number of valence electrons that you have.
So we just said that nitrogen has 5 valence electrons. 5. And remember I said the goal of every atom is to have 8? Well, let's look what 5 looks like. So if you were to write what's called the electron dot structure of nitrogen, which only shows the valence electrons, you would write the symbol for nitrogen and you'd put your 5 electrons around it. You would have them paired up. So a total of 8 around, but you don't pair up until you have to. It looks like this. 1, 2, 3, 4. Now we pair up. 5. That is the electron dot structure. Now if you look, you have 1 electron here that isn't paired. That means it's in an orbital by itself. This one's in an orbital by itself. This one's in an orbital by itself. But it can have, each orbital can have 2 electrons. So it can add electrons in here. Chemistry can occur because there is space for other electrons to come in. So nitrogen may fill up that space by either sharing its electrons, or it could steal it from somebody. It needs 3 electrons. So now let's look at magnesium. We said magnesium had 2 valence electrons. 1, 2. That's what its electron dot looks like. Selenium, we said, had 6. What does it look like? 1, 2, 3, 4. Now we can start pairing up. 5, 6. Doesn't matter how you pair them up, as long as you don't pair up until you have to, because this is a 2-dimensional representation of a 3-dimensional space. Okay, let's look at argon. This is what everybody wants to look like. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is what everyone wants to look like, and none of these do. Nitrogen, in order to have 8 around it, needs 3 electrons. Magnesium, in order to have 8 around it, it needs 6 electrons. Or you could get rid of these 2 electrons, and then you go to a full shell because now you look like the noble gas above it. Selenium needs 2 electrons. Argon is happy the way it is. Every single one of these elements wants to have the same number of electrons as the noble gas closest to it. That is its goal. They're trying to emulate the popular kids. Nitrogen is still going to be nitrogen because it's not changing its protons. All it wants to do is have more electrons. Is that so much to ask for? So nitrogen is going to do what it can to get more electrons. It's going to react. It's either going to react or it's going to steal. So let's look at let's see what it looks like when it steals. Okay, all atoms want 8 electrons. So nitrogen needs to gain 3 electrons in order to have 8. Okay, so if it were to gain 3 electrons, its noble gas configuration before, when it's just nitrogen, looks like this: 2s2, helium, 2s2, 2p3. If it gains 3 electrons, it now looks like this: helium, 2s2, 2p6, because it gained 3 electrons. Where did those 3 electrons come from? It could have come from aluminum, let's say. But what does that look like, though? Nitrogen now gained 3 electrons. So remember we said nitrogen is neutral if it has the same number of protons as electrons? Well, now it doesn't, because the protons didn't change, and now it gained 3 electrons. So now nitrogen has a charge of 3 minus, because you gained 3 electrons. Electrons are negative. So now you have a charge of -8 for your electrons and a charge of +5 for your protons. So overall, your nitrogen is now negative, N3 minus. It went and stole 3 electrons from somewhere, stole them, shared them, did something, but it gained 3 electrons. That is called an ion. Anything that is charged is called an ion. When it's negatively charged, it is called an anion. Okay, let's look at magnesium. Magnesium needs 8 electrons too. It has 2 paths to get 8 electrons in its outer shell. It can gain 6. It can gain 6. Or if it loses 2, then it goes up an energy level and it's happy again. It's much easier to lose 2 electrons than it is to gain 6. Much less work. Remember, these atoms are lazy. They don't want to gain 6. They would rather lose 2. So it starts bartering off its electrons. It'll say, I've got extra electrons. Who wants an electron? I've got extra electrons. Who wants an electron? Nitrogen might come along and says, you know what? I need an electron. Why don't you give it to me? I'll take it. Okay, so then magnesium is going to lose 2 electrons. When it loses 2 electrons, it goes from this configuration, 3s2, and it becomes just Ne. It loses 3 electrons. Loses. So now magnesium still has, oh, there's a typo here. It should say 2 electrons, not 3. That's a typo right there. Magnesium still still has the same number of protons, but now it has two less electrons. So you got more positive than you have negative. I'm going to fix that on the slides on Schoology. You need 2 electrons. So it becomes a positive charge because you lost electrons. So now you've got more protons than electrons, more positive than negative. This is an ion, but its configuration now looks like this when it gains it. So let's look at selenium. Selenium has 6 valence electrons. It needs 2. If it were to gain 2 electrons to become 8 valence electrons, it now looks like this. But it's got a charge of -2 because it gained 2 electrons. That's all. I'm going to fix this. This right here should say 2 electrons. It didn't gain two, this is because I copied it from up there. It lost 2 electrons to become neon. Okay, that's all I've got for you. Thank you.